My name is Nick James. I'm the Amplifier Product Manager for Amatec CTS. Today's webinar will last approximately 30 minutes and there'll be an open Q&A session. So if you have any questions you wish to ask during the webinar, you can drop these into the Q&A questions dialog box, which you will find in the top right hand side of your screen. So let's begin. Amplifier selection by application. What should be considered? Classes of operation are defined in terms of the amplifier's internal transistor bias mode, or the percentage of time during which the amplifier is amplifying or conducting power. A conduction angle of 360 degrees means that the amplifier conducts over the entire input power cycle, whereas the conduction angle of 180 degrees means the amplifier only conducts over half of the input cycle. A high or longer conduction angle means higher linearity. This translates to a more precise reproduction of the input signal at the output of the amp. However, high linearity can come at a cost of low efficiency and higher temperatures. So an amplifier with a 360 degree conduction angle is known to be biased in class A. If the amplifier has a 180 degree conduction angle, it's known to be biased in class B. To conduct for a full cycle, class B amp transistors are configured in a push-pull configuration. The issue though is the crossover distortion at the crossing point between each half of the 360 degree cycle. A compromise between the two is the class AB amplifier. This is a combination of class A and B, surprisingly. This allows for both halves to conduct at the same time around the waveform's crossover point, eliminating the crossover distortion associated with linearity problems, leading to a reasonable linear performance at a better efficiency. Due to the large amount of non-linearity they create, Class B amplifiers are generally unsuitable for RF applications. So most, if not all, CW RF amplifiers are either biased in Class A or Class AB. At first glance, a Class AB amplifier seems to have several advantages such as lighter weight, increased efficiency and reasonably linear performance. However, they are not suitable for all applications where a really high linearity is required. Plus, they can be more susceptible to high vswr conditions, which can lead to damage to amplifiers. So we know a chosen bias can affect the overall performance of an amplifier, with Class A offering the most accurate reproduction of the input signal, lower harmonic performance, have no crossover distortion and offer strong VSWR protection capabilities. However, this does come at the cost of lower efficiency, requiring a higher AC power input and will generate more heat. Class AB amplifiers are more efficient, can offer lower junction temperatures to the internal transistors and are typically smaller in size. This comes at the cost of linear performance. So although Class AB amplifiers are suitable for many applications, such as EMC, they are not suitable for all applications due to their degraded linearity performance. They are more susceptible to VSWR damage, and in some instances of poor design can still suffer from crossover distortion, which can lead to signal impact on signal integrity. Aside from the bias conditions, the important specifications we need to pay attention to are listed in this slide. Small signal gain, which is the ratio of output power to input power. Gain flatness, variation of gain with frequency. Harmonics, the difference between the level of fundamental or wanted signal and any unwanted internally generated signals known as harmonics. Saturated power, the maximum amount of power that can be output at a given frequency. This is expressed in dB with reference to 1 milliwatt. Linear power, or P1 dB, is described as the output power at which the gain has dropped by 1 dB from its small signal level, often referred to as its P1 dB point. Load VSWR performance. VSWR, or voltage standing wave ratio, is officially the ratio of the minimum to maximum voltage along a transmission line. This is effectively a measure of the match to the load. The load VSWR performance is therefore the tolerance of an amplifier to a mismatch condition. VSWR varies from the perfect condition of 1 to 1 to an open or short circuit condition of 1 to infinity. When considering amplifiers for pulse applications, the following specifications for the pulse requirement should be considered. The rise and fall time. The rise or fall time is defined for the leading or trailing edge of a pulse, measured between 10 and 90%. Pulse width, the maximum defined width of the pulse. Pulse rate, The pulse repetition rate, or PRF, is typically 100 kHz maximum for EMC applications. Some other applications, though, require higher PRF rates. RF delay. The difference in time from when the TTL pulse trigger is applied to when the RF pulse is present on the output of the amplifier. Pulse on-off ratio. The RF pulse on-off ratio, or signal to noise ratio, for a TWT solution can be as high as 80 dB. This is achieved by switching off the beam current for each pulse, so the noise floor of the amplifier is reduced with the beam being biased off. Pulse-to-pulse jitter. Deviation and variation from the leading edge of each repeating pulse. Pulse width jitter is the deviation or variation in the pulse width for each repeating pulse. Duty cycle. The time it takes for a given signal to complete an on-off cycle and is defined as a percentage, or in simpler terms, can be defined as the amount of time or percentage the signal is on. As mentioned earlier, most solid-state amplifier datasheets list two types of output power: saturated power and P1 dB power. It's very important to pay attention to these specs in relation to your application. For instance, if you require linear performance from your amplifier, then the P1 dB power should only be considered. In this example, this would be the red curve, which indicates the maximum amount of power the amplifier can produce when the gain is in error by 1 dB for any given frequency. If the datasheet does not list the P1 dB performance, then this should be considered, as it may not meet your application requirements. The term linearity has been mentioned many times, so what do we mean by this in relation to amplifier class and bias? The two charts show different amplifier performance expressed as gain error and is a good example of good and poor linear performance. Left is typical of a Class A amplifier. The perfect state does not exist, so there will always be either some slight gain expansion or compression from the 0 point. To maintain signal integrity, the gain of the amplifier should never exceed plus or minus 1 dB before its specified output power is achieved. In the case of the chart on the left, this is 200 watts or 53 dBm. So as you can see, there is some slight gain expansion up to the point where the specified 200 watts of output power is achieved, after which the amplifier compresses to its 1 dB point at around 300 watts. The performance of this amplifier is considered to be very good. The right graph can be typical of an A-B amplifier where the linear performance is not considered to be as good, as the gain error, in this case gain expansion, exceeds plus or minus 1 dB before the specified output of 1000 watts or 60 dBm is achieved. This type of performance can affect signal integrity or affect the signal integrity of the amplifier. However, this performance could be considered usable for a limited amount of applications, where the performance of the amplifier on the left would be considered usable for all applications. Maximum power transfer of energy from an amplifier to a load occurs when the impedance of the load is the same as the impedance of the amplifier. In this case, these two impedances are said to be matched, and if you had a lossless transmission line, all of the output power generated by the amplifier would be absorbed by the load. This represents the ideal one-to-one situation and provides maximum power transfer to the load. This is the ideal condition, but the reality is it's never likely to happen. So what happens if the load impedance is not the same as the amplifier impedance? In this case, some of the forward power from the amplifier that's transmitted towards the load is returned back into the amplifier. The relationship between the forward reflected power can be quantified as a ratio of the minimum to maximum voltage or standing waves on a transmission line between the amplifier and the load, and is an effective measure of the match. This is specified as a voltage standing wave ratio, or vswr, on many amplifier datasheets. High reflective power conditions or poor match between amplifier and load can damage certain types of amplifier, so it's important that amplifier manufacturers design their products to be protected against this. How they do this depends on the class of amplifier and design. Some Class A amplifiers are 100% hardware protected and do not require additional software to control gain or fallback in high VSWR conditions. as is required by some Class A/B amplifiers. Note, you can have a high vswr condition at low output power levels, which most amplifiers can handle. It's only when the amount of reflected power exceeds a certain level that it becomes an issue and can cause damage to the internal transistors of the amplifier. So one thing to be mindful of is that all amplifier manufacturers, including us, state in their datasheets that their amplifier products have infinite vswr performance without damage against all phase angles. It's important to read the vswr spec and the small print as to how they achieve this. Is the gain required to fold back? If so, at what level or at what vswr level? Then you need to ask yourself, does this meet your application's requirements? As an example, if you had, let's say, a delamination process application that requires the amplifier to drive into a poor load, providing constant power without suffering any foldback or loss of floor power, then a Class A amplifier product would be required. This is because Class A can be designed to protect itself using hardware without the requirements to fold back, so it can be quite happy driving continuous power into an open or short circuit load condition. Most amplifiers that require some type of foldback protection circuit are biased Class A/B. Though are suitable for many EMC immunity applications, one thing to be mindful of is the growing popularity of reverb chambers. These, by their very nature, generate high vswr conditions, so Class A products are probably the preferred choice. When the gain of the amplifier is required to fold back, to protect itself, the amplifier uses software to control this function. If the power detector internal to the amplifier is not quick enough to detect the reflected power, and power spikes can get through the protection and damage the amplifier, so it's important to pay attention when connecting and disconnecting the amplifier to the load. A misconnection is a common cause for this type of damage, where the signal is switched on, the amplifier is presented with what effectively amounts to be an open or short circuit load condition, and doesn't have time to react to this condition, allowing power through its protection and damaging the internal RF transistors. There are many different types of amplifier available on the market today, from different technology, solid state to TWT, different functionality, CW or pulsed, to different fits and forms. All of these factors need considering when making an amplifier selection to meet not only your application requirements but also your environment requirements. Solid state use ever-evolving RF transistors rather than tube technology. These include gallium arsenide and the more commonly used gallium nitride. As these devices have different properties, they can affect the amplifier design, size, and efficiency. So it's important for the user to select an amplifier based on specification rather than the internal technology that was selected by the manufacturer. Solid-state amplifiers can produce a specified rated power either continuously or pulsed, and are available in many frequency, power, fit and form combinations. The relationship between frequency and power is that more power is available at the lower end of the spectrum and then gradually declines as the frequency is increased. For pulsed operation, CW amplifier can have a duty cycle up to 100%, though it's important to note the output power will diminish at these high duties. Higher power can be achieved at lower duty cycles as the efficiency of the amplifier improves. At selected powers and frequencies, TWT still have a size, performance and efficiency advantage over developing solid-state solutions. The tubes are powered from high-voltage power supplies, typically up to 10 kV, and require a startup procedure of a few minutes to warm the cathode emitter before operation. Like the solid-state CW amplifier, they can produce the specified rated power continuously. TWTs tend to produce higher harmonics, and so harmonic filters are sometimes required for certain applications, and are usually an optional extra available from the manufacturer. One point to note though is that TWTs have a typical 25 dB higher noise figure than the solid-state solution. This can have a significant impact when you multiply by the bandwidth. PostTWT are only capable of producing pulse power. The design is configured to focus the beam current at the specified voltages. These amplifiers can modulate a CW signal themselves using grid modulation. They can also accept pulse-modulated signals but require synchronization. The beam must be limited to a certain duty cycle, typically 6%, so the internal components of the TWT do not exceed its specified ranges. If it's run at a higher than specified duty cycle, the TWT components will overload and a failure will occur. This is because the closer the TWT is forced into a CW operation state, the higher the power dissipation requirement becomes, causing the tube to eventually burn out. At the specified duties though, PostTWT can produce power in the kilowatts range and are ideal for EMC immunity and A&D applications. In the same way that it is possible to produce PostTWT power amplifier, we can also produce pulse solid-state amplifiers, which are typically biased in Class C. For Class C pulsed amplifiers, the same duty cycle restrictions can apply, meaning the specified power level and duty cannot be exceeded. Due to their high efficiency, Class C pulsed amplifiers can achieve much higher output power than their broadband CW solid-state counterparts in a smaller physical size. Of course, all of this, as with other amplifiers, is frequency dependent. For EMC testing, amplifiers are required to generate the field strengths and currents for immunity testing against the commercial, sub-6 GHz, medical, automotive and military standards. These standards define the requirements for the measurements, and as a result the requirements from the amplifiers such as output power, linearity performance, CW or pulsed operation. As an example, the 80% AM modulation required for the commercial IEC 61000-4-3 standard is where we would focus on the P1dB performance of the amplifier, whereas the peak conservation required for automotive standard ISO 11452-2 saturated power can be considered. Due to the wide range of requirements from all the different industries, a combination of solid-state and TWT amplifier often provide the best technical and cost-effective solution. Current 5G backhauled infrastructure below 6 GHz uses a modulation scheme based around OFDM, orthogonal frequency division multiplexing, which combines the benefits of quadrature amplitude modulation, QAM, and frequency division multiplexing, FDM, to produce a high data rate. With this high data rate, a resonance-free bandwidth between the tones is required from the amplifier system to achieve promoted 5G performance. The performance from a 5G system can be analysed by looking at the signal intermodulation properties. In this example, IM3, IM5 and IM7 shown on the graph that need to be resonance-free and without the amplifier collapsing due to the wide bandwidth. The attached chart shows the average IM levels from a 6G amplifier from our TESIC CBO product line set to 3.4 GHz with an increased tone separation between 10 kHz and 1 GHz with a resonance-free response. A typical OFDM modulated signal actually appears as a noisy band-limited response in the frequency domain, so IM measurements are a quick way to display the amplifier linearity over a wide bandwidth. As a result, this type of application requires Class A accurate replication of this complex modulation to test the infrastructure components. Additional TWT applications. Aerospace and defense applications such as communications, electronic warfare, EW, and radar is where TWT are still unparalleled in performance. CW-TWT covering the L to KU bands and PostTWT covering the S to KA bands are used for surveillance, radar jamming, targeting systems and short-range search and rescue applications. Threat simulators and SATCOM frequencies also fall into this domain, along with high-power component testing and high-power, high-energy physics tests. The chart in this slide gives a good visual example for the power and frequency offering from the different types of amplifier technology. It's also important to remember in many of these applications, fit and form are just as important as the frequency and power requirements, as not all amplifiers built from the same technology, covering the same frequency and offering the same power output, are designed and built in the same fit and form. So in conclusion, amplifier class is important dependent on the application, as it can affect the linear performance of the product. Frequency and power requirements. Which technology will offer me the most cost-effective, best performing solution to meet the application's needs? CW or pulsed. Which type of power is actually required? vswr considerations. Will the amplifier be expected to drive full power into a poor vswr condition without folding back? Fit and form is dependent on the environment the amplifier is to be used in. In closing, always read the specs, as RF power costs money, and if there's any doubt, our experts at Amplifier CTS are here to help. Okay, so let's take a look at some of the questions that have been asked. Is P1dB important to my application? Well, as explained in the webinar, P1dB basically is the point at which your amplifier is linear to. So if you're looking for an accurate reproduction of an input signal, up to your P1dB point is where your amplifier should be accurate. Above this, the amplifier will generate more power, but the closer it gets to compression from its P1dB point, the less accurate the replication of your input signal will be. So if you have complex modulation signals, up to its P1dB point is where you can use your amplifier too. vswr. So yes, vswr, how important is it? It's very important. Amplifiers cost a considerable amount of money, and we spend a lot of effort in protecting the amplifiers from reflected power because it can damage the internal transistors, which can result in a very costly repair. So we try to make the amplifiers as robust as possible. Different classes of operation enable us to offer different types of protection. As with a Class A amplifier, one of our designs is completely hardware protected. What I mean by this is any amount of reflected power at any given speed back into the amplifier will not damage the amplifier. If the amplifier is designed under a Class A operation, then we have to employ additional protection because too much reflected power can cause damage to the gates of the drains of the transistors. Okay, intermodulation wide. So intermodulation testing, or space between the tones for 5G comm. So with the new 5G applications that are coming onto the market, to offer the speed for 5G cellular comms, the space between the transmit and receive tones need to be as wide as possible to enable as much bandwidth space for the signal. One of the problems that a lot of amplifiers have is the amount of space between the tones that is required. 200 megs is pretty common. It's getting wider. Our amplifier has been tested up to 1G and the signal integrity is good and it doesn't collapse. So one of the challenges for amplifier designers is to ensure that the bandwidth at which we are required to operate, the amplifiers don't collapse. Okay, so if your question hasn't been answered, then don't worry, we will be responding to all questions electronically. If you have any additional questions, then again, please feel free to respond to one of our invitation emails. I'd like to thank you all for your time and for attending this webinar, and